Super excited to show you what kind of crazy stuff we built in the past few months. And specifically, we want to talk about, well, controlling robots in user-hostile and dark environments.
I think you mean controlling them the same way as NASA does.
Yeah, of course. I mean, this is JPL town. You see the ads everywhere. You know, build robots, not meme apps. I love that. If you have kids that like robots, definitely let them build stuff.
So, hello everyone. My name is Adrian. I'm a solutions architect at HashiCorp, and before that, I used to be my true passion, a site reliability engineer.
That is nobody's true passion. Nobody wants to get paged at 3 in the morning.
It's fun. I promise.
It's a lie. Well, hello everyone. My name is Kerim Satirli. I'm a senior developer advocate at HashiCorp, where I get to tell people about best practices and how to build them, implement them, but I don't get paged, which is a part I love about my job. Before joining HashiCorp, I worked on industrial IoT for the Amsterdam airport, which sounds super glamorous, but all we looked at was sewage pumps, which is a less fun part of IoT. So last year we presented something here, a concept called batch computing. The AE is on purpose because it's a badge, but it's also an edge compute device. We had a Raspberry Pi Zero in there. Really badly supported Python libraries, incredibly bad code. Not ours, but the code we started from. And I think we learned some important lessons. There is a distinction between the smell of a molten MOSFET and one that's currently melting. If you understand that joke, I'm so sorry, because you probably also have the puncture holes on your fingers. And so we thought, you know what, this was an absolutely horrible experience, so we're going to go and make it more horrible. Instead of going towards languages that embrace you, that welcome you with warm, welcoming communities, we figured, you know what, we'll go a little bit back. We'll go more towards embedded computing, where Copilot gives you stuff and then just laughs at you because, like, what are you trying here? Like, I don't have a data set that can help with the question you have, but the code looks good. So I want to talk a little bit about the goals of what we're building and what we're planning on building. At the base, we want to have something really simple, right? Remotely control a device. We do this all the time. I mean, I'm currently remote controlling my slides here. Well, we're kind of messing with the camera feed by switching the light on and off. You have a device, you give it instructions, it does what it's intended to do, it's great. Love it when that works. Doesn't always, right? If you've written enough code, no matter what kind, you know that the code sometimes does its own thing, and things get harder. And here's the really hard part. We want all of our instructions to be followed all the time. If you do work with ChatGPT or any other prompting system, you know this. You know, you specifically say, follow my instructions, give me all the goods, tell me what day it is today because you want to have the most accurate data set. When you work with robots, 3 laws of robotics, very important. But even so, the machine might not always do what it needs to do. I know this is starting to get a little bit theoretical, so let's make this more practical. Ghost in a machine is a real thing. Sometimes, despite all the best planning, things don't go as planned. Just like what happened 2 days ago, Friday. It's already Sunday. Man, time flies. With the Athena lunar lander. It got the lunar part right. It made it there. Struggled somewhat with the landing part. To give you an idea, these are the legs. When they're pointed upward, it's not optimal. Mission has since been concluded, which as an engineer, I feel really bad for these people because you plan this for months, for weeks, for years. And then because one thing goes wrong at the end, this is all you get. It's pretty cool wallpaper though. It's a good reminder of things that can go wrong that you have zero control over. Not as cool as the story of something else with metric versus imperial. We'll get into that later, but definitely a lot of fun. So Adrian and I work at HashiCorp. One of the tools we make is Terraform. And if you've used early Terraform, you definitely know that you would tell it, give me a web server, give me a database server. Everything would look good. And on the first run, well, computers don't always do what you tell them to do. So maybe on the second run, it worked out. Well, so let's update our goal. Let's make it more fun. We're going to build a robot, do something fun with it, do something potentially useful with it. I mean, anytime you're learning, it's useful. So that's our primary goal. And what we really want to do is start somewhere, empty canvas.
As engineers, we really like greenfield projects where we start from scratch, we do whatever we want, there are no constraints, no limitations, nobody has restricted us on the language, architectural choices, etc., etc. But they're not always the best approach, because even when doing this for fun, like we are, there are timelines, like a conference, and timelines mean deadlines, so we can't just spend years working on this and developing everything from scratch in Rust, even though we might like to. So, what's the alternative?
Brownfield.
Yeah, sometimes a good alternative, but there is also another one which we chose, which was better for us, probably, hopefully, commercial off the shelf. So starting with something which already exists, which you can acquire from a hopefully reputable vendor, which saves you time, prevents you from reinventing the wheel, and everybody does it. Like the US Navy does it when they buy ships. Sometimes they try to, when they're forced to. NASA does it, like they've been using an IBM-designed single-board computer from IBM, which I already said, for the past 2 decades, and of course the ISS uses Lenovo ThinkPads, which you've probably seen on videos. So yeah, that's what we decided as well. We bought some hardware off the shelf, which looks like this.
Before we dive into our hardware, quick note on that single board computer. The RAD 7050 is indeed, as the name implies, very rad. 370 grand for 110 megahertz CPU, but you can absolutely overclock it up to 200, get all the speed out there. And we're all laughing at this, right? Because, yeah, the ESP32s that we use for our robots have 240 megahertz. Yet we're talking about hardware that's been in space for 20 plus years, on plenty of missions, still works. I mean, if that's not the reliability we're aspiring, then what the hell are we doing? So last year we started, that was one too many. Last year we started building this project with our first rover. We call it Pathfinders, obviously an homage to the actual Pathfinders that were sent up at one point. Started out with a pretty cute system, 4 wheels, very nice. Some younger members of my household decided to stick rubber ducks on it to make them more personal. I like their identity to be based on the MAC address, but we do what we can. But ultimately realized 4-wheel drive does not really work, and there's a reason why all the rovers have 6 wheels. So that's where we went. Of course, the lowest bidder won. So we have 6 wheels, but only 4 wheels are actually powered. But we still get a 25% bigger footprint. This is a render of the actual device that we have. So you'll note a couple of rails on top. Well, guess not in this render. Rails on top for cameras, robotic arms, whatever we want to put on there. Given, of course, it's less than, was it 2.5 pounds? Or 2.5 kilos if you prefer metric. So, biggest thing, really, for all of them, we based them around ESP32 because that gives us, access to a lot of code that we don't have to write ourselves. Always beautiful. The whole Arduino ecosystem is really good at giving you access to all the stuff that you don't want to figure out by going through hundreds and hundreds of spec sheets. Bluetooth, Wi-Fi, we're not using Bluetooth, not very reliable for what we want. And it's easier to pre-seed Wi-Fi stations than doing constant Bluetooth handovers. The real beauty here is access to host computers that you can install. In our case, Raspberry Pis, Jetson Nano, Jetson Orans. So you can do a little bit of AI processing at the edge, provided you can give enough power to those devices. The more processing you do, usually the heavier your hardware gets, which has more strain on the system. And we're only powering this with 3 of the standard industrial batteries that you come across everywhere, that TSA is absolutely a huge fan of when you bring many of them in your suitcase. Seriously though, don't ever do that. These are hand carry-on only. And let them know, because they show up on the system. So, GPIO, standard interface, right? All the good stuff. Ability to power Raspberry Pi directly, which is very nice. The Jetsons, a little bit harder because they require a little bit more power. Support for LiDAR, like the actual board in there has a connection interface that allows us to take LiDAR data and process it. And of course, plenty of expansion ports if we want to drive a gimbal or an additional camera or whatever else we need. And like I mentioned, 4-wheel drive on 6 wheels. When we got this thing, beautiful packaging, right? Not Apple inspired, but definitely higher end for IoT devices. We were like, well, this looks great. Let's unpack it. You look at the box and the demo code that comes with a little QR code, like please scan this link, it gets redirected 6 times, and you end up there. Yeah, that code, we'll talk about that part later. The care that went into designing the shell was definitely higher than the care that went into designing the code, and yeah, deadlines. So hardware, easy part, right? I mean, at this point, 3D print whatever you need, get to the software part. Written in C++, which if you grew up in the PHP era like me, you've never touched. It's a steep learning curve. Code had some imperfections, I want to say. Most comments were the prompts that were used for ChatGPT, written in Mandarin, and they were also the only comments in the code. But luckily, throw those prompts into a translation tool to figure out what the prompt said, figure out what the original intent was. It almost feels like you're bonding with that engineer. It's beautiful. Arduino ecosystem helped us greatly in terms of helping understand, why is the wheel moving the way it is moving, or why is it not moving? It's probably the more realistic outcome. And you learn fun things, like normally I would think a wheel, has 2 states, a motor has 2 states, either you spin or you don't, or you move, doesn't have to be spinning. In our case, the software interface was using an LED library, so we were using pulse width modulation, and basically pulsing the wheel to keep going, which when you have a lot of logging in your code, makes it very hard to understand what's going on. So, of course, like any true engineer, we took all that code, refactored it, made it better, built a Terraform provider around it, made the API actually more fun to use, and figured, infrastructure as code, Terraform, yes, here, but why not do something that we could use anywhere? And how do you go about building the API? So, kind of jumped into that a little bit. And then comes the fun part. Once you have your first goals completed, right? The thing moves when you tell it to, the thing stops when you tell it to. Life gets really good. You feel great, especially because you wrote code that never worked in the first place. Well, what can we do? Well, obviously, we add cameras. In our case, we're currently experimenting with a system of 4 cameras, which gives us around 300-degree vision, because of the design of the device, we don't get full 360 and the placement of the cameras, but still enough for us to see what's happening. And then, of course, we like edge orchestration. Not everything has to run on the ESP32s. So anytime we can go to a more well-understood system, like a Raspberry Pi, anything that we want, or the Jetsons, we can fall back to Nomad, which gives us orchestration at the edge. And when you think about it, remotely controlling a robot is fun, right? I mean, from early age on, like age 3, 4, whenever you get your first remote-controlled toy, car, whatever, even the ones, our daughter is 2, she's got one of those toys that interacts with her without a remote control, simply by gestures. Very cool. Also has a LiDAR in there. Up to the age of, how old was he? 45, right? When you're a remote mobility engineer at NASA, aka the person that drives these robots on Mars, seeing something move when you tell it to across a long distance is always going to be magical, especially the first few times, especially when it's across 140 million miles. So that's what we want, right? We want to move things around, build a set of movement instructions, do something. So, took our graphing paper, started drawing a little path, and figured out, what is it that we can do here? How do we do navigation? How do we get from A to B? And what system should we be using? And that's really the hard part. Most of the time, when we think of race cars, toy cars, anything, you have a joystick. You have a wheel, you have something that is well understood. But what do you do when you don't actually see the device? When you have to infer what you want to do from a map that you have, which might not be live updating. I mean, 13-minute lag delay between us and Mars on a good day. On a bad day, slightly more. And that bad day, once it starts, it lasts for a while. So before looking at space, well, maybe we look what we do here. So we looked into navigation systems used by submarines, which most navies in the world are not super keen on telling you about. But luckily, there's some research that we can look at. And so, first one, sonar and LiDAR, right? Basically, you could use LiDAR underwater, provided your sensor is underwater as well. Has some upsides, has some downsides. So, makes you think, like, well, what are we gonna do with this one? Light pulses, sound pulses, okay, that could be annoying. If you have LiDARs that go at super high speed, you actually hear them. In our testing, that was not joyful hearing that in the lab the whole time, especially if you misconfigure them or if they drop off the table, or as NASA calls it, is it the unscheduled rapid deceleration. These are all very important terms. It's also less painful than, say, you crashed it off the table. But because of the design of the device, we couldn't actually guarantee that LiDAR would see all the obstacles. There's a reason Tesla has their LiDARs in the front of the car and not on top, because at the top means it doesn't see anything that's below it. Not anything, but like anything that's too small. And we ran into that problem many times, quite literally. We miss obstacles that the code or the sensor just couldn't see. And it's also not a great system, sonar specifically, to use if you're being hunted underwater. Not a concern for us, definitely worth mentioning. We want to give you a full overview, everything, right? Option 2, much easier. Submerged beacons or beacons in general, sat-nav, very solid. GLSS systems work for a reason, but they're costly. Seeding this room with beacons is going to take a lot of prep time for us, and we're just talking about one room. Also not optimal. Putting something on the ceiling, well, if they don't want us to switch off the lights, pretty sure they don't want us to climb on the ceiling, so also makes it hard. Which really brings us to, well, basically one final option that we can look at, which is what submarines do when they don't have access to maps. And it's also the most cool name. dead reckoning. Basically, a vessel calculates its position by looking at their current position, location, speed of travel, and direction of travel. Works generally well if you have some understanding of how the planet or how the body of water that you're in works, but errors accumulate over time. In our case, we'll use this because we had the map that we showed you earlier, and really, we kind of know what to expect, right? So we'll build with that. This is the hard part, though. The accuracy depends on a lot of different variables. If you've done a lot of programming, none of which interfaces with real hardware, you'll never have felt the joy of a motor that goes the same distance twice in a row after you handed it off to a colleague who has no idea how to treat that thing with respect. All those variables really, really affect the outcome of the movement plan. And, well, errors accumulate. So before defining our schema, took our map, threw it into Illustrator. We looked at a couple of mapping tools, and we designed pretty much the same track, and then mapped out how we want to move around it. I apologize if you're looking at this because of the light. The brown line might be a little bit hard to read, but imagine it's there, and imagine it's a drunk raccoon driving a car on a track, hoping to stay on said track. And you'll see we've got a couple of tight turns that almost give you, negative 90-degree turns that will barely keep you on the track. And we want to have all of those problems to figure out, can we make this move? And spoiler, the first version did not. The first version did not respect the sides at all, but we got amazing round trip times. The whole distance, given the optimal speed of the device, should be covered in about 40 seconds. We hit the goalpost after 7 seconds because the device just made a quick loop and went there, and that was it. Now, of course, if this was a race, you could take this shortcut. Not very sportsmanlike, but at least you're first, and you're saving yourself a little bit of gas there. And gas prices are rising, so it's fair, right? Not what we wanted, though. I think you described it as we shouldn't have any shortcuts like that in a hostile environment. Hostile being anything where, what if the white space there is actually a lack of road? What if there's a cliff, something that we don't want to crash off of, edge of a table? So we need to drive on the pre-planned track and make that happen. And so we looked at our track, mapped out a couple of waypoints. In our case, I think 34. And it's really simple, right? Using dead reckoning, we could zoom out a little and think of, okay, so what do we need? We need a direction of movement. We need an angle or bearing or something. And we need a distance. And so if we pop this into a JSON schema, because obviously how else would you describe this? Well, we got a name of the movement plan. Really simple reason. We wanted to see how one movement plan compared to another. And unique identifiers like that, or identifiers like that helped us. And then a couple of steps. So direction, easy, right? Forward, backward. Could be confusing depending on how you orient the device, but we'll go there. And a distance. You notice distance does not have a unit on there, which is a mistake that we thought we could correct. We could not, but we'll get into that. I think you're going to talk about that later. So 3 question marks is obviously one of the coolest keys that you can use. It's not very descriptive, so let's experiment a little bit here. Option 1 is we use bearing. Sounds cool. Doesn't really work though. If you look at where the 0 is to the green arrow, you'll notice that we're going to the right, but we're at 45 degrees. That's because our true north is not in the direction of travel. Now, this is not a problem on any planet that has a strong magnetic field, because your compass will always tell you with a high degree of accuracy how things work. On Mars, that would be a problem. Magnetic field is too weak to use actual magnetic navigation. So in our case, that's out. Much weaker than Earth's magnetic field, only on the South Pole, I believe. Would it be barely strong enough? Yeah, and we don't want to build stuff that may work if you're on the right location. We want to build stuff that works consistently. Not that we're getting there, but yeah. So we'll switch it to angle. Dead reckoning goes well with angle, and things get a lot easier. If you look at it, we're traveling to the right, our device is oriented to the right, so there is no angle change. If we add a second step on there, which gives us this one, we have an angle of minus 50 degrees because we're turning to the left from the viewpoint of the device. We travel forward, distance of 10, and it's easy. Repeat that about 32 more times, and you'll have the full track defined. Joke's on us. The chip we used was so cheap that we could, at most, consider a payload of 20 steps before the CPU would give us a guru meditation overflow error. So that was great. But in theory, had we invested in more expensive chips with more than 2 megabytes of application storage, we could have made this work. And of course, like any good engineer, we drew it, we tested it, we wrote it out, we documented it. It's very important, because only that way could we have actual conversations about this with our whole team. So we figured, well, we've got this movement plan. Angle and bearing is very confusing. There was a period where we didn't touch this for about 2 months, and when you come back to a project like this, your head goes to what it knows. I think you went to bearing, and our code just didn't work because the code was expecting angle. So having it documented when it's fresh on your mind, free career coaching, do it all the time. It makes you a better engineer. Future you will thank you, and past you will also be grateful, because you're going to be looking back at this project not thinking like, why did I do this? But you'll understand why you did it. But angle, direction, distance, we're not taking a lot of stuff into account here.
And even with that not very complicated instruction, there's a lot of things that can go wrong, like really a lot, and we went through a lot of them. So the first one is the distance traveled. First you need to have a common unit of that distance, like Kerim alluded to earlier. When you have one contractor using Imperial and NASA expecting metric, fun stuff can happen, like maybe you lose a spacecraft. In our case, it just runs off the table, so it's not the end of the world, but still, if we can avoid it, it's great.
But it was the end of the table.
Yeah, but we didn't maybe lose it entirely. Like, we could salvage parts of it, so not the end of the world, but still, it's important to have a common unit that everybody knows, understands. You preferably have it in the specification directly documented so that everybody knows what to expect. The movement doesn't happen in a vacuum, depending on the environment, on the carpet, the table, if there's rain, if the humidity is different, the distance traveled will be different, potentially. And also, the rover has inertial measurement unit, so it knows what position it is in, and depending on the position you're in and the environment that you're in, that might or might not be accurate. So you can have also some fun stuff there to account for. So Then the power of the motors also depends on the battery level. So half speed at full battery and half speed at almost no battery are different speeds. And it's not documented what those speeds are, and of course they also depend on the carpet and the table and etc. So we had to test all of this and account for it in the code, which, yeah, again, not necessarily obvious. Also the device itself, the wheel fairing on the initial version wasn't a very good quality, so it was plastic. So it was quite easy to damage, so we tried 3D printing stuff, improving, but yeah, wasn't enough. This one is full metal, so survives a little bit better when we have unscheduled downward motions and full decelerations, runs off the end of the table. And so all of these things have to be counted in the software that we write. Like there is no magic easy way, say run at a consistent speed or account for the carpet friction. So this is part of the environment. The traction, depending on the type of surface we have, will be wildly different, which was fun to discover. Like, of course, it's obvious in hindsight, but not always when you're there. So also the environment, in this case, we have a carpet, we have the cable. The way that the cable is, depending on the positioning of the rover, the LiDAR might not see it at all and might not know that it's something to avoid. In this case, maybe not, but if it's something bigger like a pen, it could be an issue. And of course, there is also inference, like we're in a conference room, there's a bunch of equipment, you probably all have phones, there is Wi-Fi, Bluetooth, and all of these cool things which result in inference. So we need to account for potential disruptions in the communication between the rover and our control unit. Yeah, handle gracefully if there's any failures around this and not just crash or run off the table if we lose connectivity for a second. And also, of course, the distance, because it's still an embedded device. Yeah, it has a big pointy antenna, but still, it won't run well over long ranges for now.
And so one good thing to keep in mind there that we discovered early in our code, when our network connection would drop away while sending instructions, the last instructions would be repeated until new instructions were sent. Which is great if the last instruction was to stop and halt and stop movement. Not so great if you're losing connection because somebody is rebooting a router or something else happens and you just can't get to the device in time. Emergency stop code is definitely worth having and building into your systems. That big red button doesn't have to be a physical button, just an API call that allows you to shut everything down. Definitely useful.
And also a dead man switch. If you lose connectivity for too long, just stop, because, yeah, don't know what's happening. So we also have, yeah, we've accounted for all these things. It was not very easy, especially in C++, especially with no modern IDEs, no ChatGPT to help really. So, but we've managed to do all of this. It took us a couple of months, but yeah, we're there. But we already have a list of improvements, stuff that we would like to do to make this even better and more fun. So, as Kerim mentioned, we've already started adding cameras. We're using cameras from Siege Studio, which can run object detection models directly on the camera itself, so it saves us some compute. So we're going to try to add, computer vision and detect objects to avoid or people to run over and stuff like that. On top of the cameras, because cameras are good, but if it's dark in the room, they won't see anything, so we're also going to improve the LiDARs, mostly their positioning and decision-making based on the information from them to better avoid any potential obstacles, or if there is a potential obstacle, go back and stuff like that to avoid driving off the edge of the cliff or a table or going into somebody or getting entangled in cables. And yeah, communication, I already mentioned this briefly. In a place like this, Wi-Fi might not work well. Over long distances, Wi-Fi does not work well. So we're considering adding LoRa for long distance communication and potentially, hopefully, more reliable communication, especially in dense environments.
Let me grab this one real quick. And so the fun part that we realized, we deployed an army of these at an event in October, about 12 of them, but they didn't talk to each other. And that's always the sad part, right? You've got 2 robots, some of them adorned with rubber ducks. We should do something fun here. So ESP now and other technologies give us access to the basics of swarm logic. So we figured, you know what? We've got 3 of them. We'll have a leader and 2 that are basic followers that just do what they need to do, which is always beautiful. But the more interesting part is, this being the bigger version. Do you want to bring her up? This being the bigger version, sometimes you don't want to sacrifice the big one with all the cameras. You want to sacrifice one of the smaller ones. So we figure swarm logic could allow us to test certain things where we bring a smaller one forward that then communicates the things it finds back to its leader. She's a little bit shy, as you can notice. A lot of people, which does freak her out sometimes.
And the carpet makes for not great friction.
Still better than sand. And so, of course, I think you want to go the other way. There we go. See, Matthew doesn't bite. The next step here is, of course, edge computing is fun, and having those small cameras be able to process what they see at the edge, very cool, but still very underpowered. There's only so much processing you can get out of a device that's $50, $60. So what we're working on is this beautiful case, about a third bigger than this case. With recent changes, I did not want to tempt my luck with TSA, so I did not bring this one. But basically what we have in here is an AI accelerator, built-in network built-in network access point, and everything else we need, which really gives us access to all the processing we need for these devices. And of course, because it's a standard computer running, in our case, Ubuntu, life gets really simple, right? We're no longer forced to use crappy code. We can just use any normal application. We've got a 10-inch display in there that you can tap, and it's a self-contained unit. Backhaul via network, which then gets provided from this device, so all the rovers can connect to it. And because we've built a couple of these, also easily connected to a LoRa access point, so should Wi-Fi fall away, should Bluetooth fall away, we can still use LoRa networks and Meshtastic and everything else. Do you want to bring her back? Yes. We, all of these were named by my daughter. This one is called Cat, for no reason other than our neighbor have a black cat. We spray painted one white, which is called Lucky because that's our other neighbor's white dog. There we go. We're not currently recording it, so we are?
Yeah, it's recorded.
Oh, right. So, yeah, I should have probably prefaced this by saying Adrian and I are aware of the laws of robotics. Our Pathfinders are currently not. They will run themselves off the table and hurt your toes if told to do so. But yeah, that really brings us pretty much to the end before we get into questions and everything. If you weren't paying full attention, you could totally think this talk is all about the ins and outs of controlling robots and all the stupid stuff you could do by improving code that somebody else wrote and bonding with somebody over the internet. It wasn't. This talk is really about building a system that is able to deal with a lot of variables that you have no idea of, the known unknowns, and very much the unknown unknowns, like, will all 10 that I ordered behave in the same exact way, given the same software and the same battery charge? There's a lot of experimentation to come to a very clear answer there. That answer is no, they won't, especially once people start lifting them up, handling them, and encouraging them to seek the tolerance limits of downward acceleration. This model is currently one of 2 that are still functional, but we do have the parts of 12 other ones. Yeah, ultimately, all of this to say that experimentation is important. We're normally dealing with stuff in the cloud, multi-cloud deployments, multi-continent deployments, everything that's very easy, very predictable. Nothing is as fun as seeing this little rug rat drive across the room and knock somebody's water bottle over. Purely hypothetically speaking. No, but seriously, once you get into challenges of like, what kind of data can I collect? How do I collect it? What do I do with that data? Collecting data is easy, right? Buy a 2 terabyte SD card, it's $200 at this point. You can collect for the end of days. But what do you do with that data? What do you do to make that device smarter? Can we turn this into a toy where if I throw a ball at it, it notices what a ball is and uses its grabber to either pick up the ball or bring it back? If you're on the East Coast, this small college, university, they do a lot of that stuff with a couple billion in funding. Turns out you can do a lot of that for less than 500. I think this one is 300-ish. With all the stuff we add on, maybe you get to a 500. There's a lot of fun that you can extract from that. So as an engineer, if you feel you need a new challenge, get into this kind of stuff, have some fun with it, and learn from it. And to give you an idea, what we already had part of the demo, the interface Adrian is using kind of looks like this. Also works with a joystick, or joypad, sorry, not joystick. That'd be much cooler. Allows us to set speeds. I'm going to set it to high speed and see if we can cause some damage.
That was the high speed.
That was the high
carpet
speed.
is really...
Carpet is not a friend. Got it. And of course, we've got a bill of materials, all the code that you need, everything. It's still crappy code. It's getting better. PR's welcome. But we do have the complete code base for this and the smaller units available. All open source, of course, because that's how it should be. Because ultimately, that's how we learn from it. And that's how we hope other people can learn from it. And with that, I think that's time for questions.
Thank you for the presentation. Just a question about, in the future, you guys are thinking of doing AI and edge computing more. Have you guys talked a little bit about Jetson Aura, Jetson Aura Nano? Have you guys tested that out, or is that something, are you guys going to stick with the ESP and just do that, or?
We're using, so first of all, great question. I'm glad you have the mic because I don't need to repeat the question, but so we're splitting the computational workload in a couple of different systems. The ESP32 is great at receiving very simple instructions, doing stuff with it. So all the movement is already connected to it. Running that under something more powerful like the Jetsons, not great, so we keep it on that simple chip. Also because if we fry it, not a big issue. The Jetsons, on the other hand, and Pis and the Pis with the AI accelerators, full-blown computers. So we let them handle the workloads we understand. So if you want to run something like, any model through Olama, we'll just spin up Nomad, run the workload that way and experiment with it that way. What we've done is we put one of the CJ4012s on there. It's like AI accelerators about this size and what is it, like 1.5 pounds probably. So it works. The device will happily chug along, but speed goes down. Plus you're now running a robot that's 300, running a piece of hardware that's about $1,000. So that's not great, which is why ultimately, in this case, what we're doing here is this is that same accelerator. As long as we have data connectivity between this case and the robots, we can do all the processing we need, especially if you switch to something like LoRa, for a simple reason that pretty much everywhere you go, unless it's an industrial plant, LoRa is not contested. So that is the approach that we like. Great question.
Did you guys ever hear of something called Robot Operating System, or ROS? And if so, could you talk about how something like this would work with ROS?
I think a lot easier. So ROS is definitely a great approach. The reason we started out with the code that's in here and started improving that is because, like most projects that you do in your spare time, we figured, you know, it's Thursday, we could have done all of this by Sunday. And that was true. That Sunday was sadly not the Sunday 3 days later, it was the Sunday about 4 months later, at which point we decided, you know, this is where we're going. We also wanted, from an engineering perspective, the challenge of figuring out a lot of this ourselves, simply because it allowed us not so much to reinvent the wheel. The whole reason this is working and driving is because we're standing on the shoulders of giants. People much smarter than us that understand a lot more about this, that build code samples and libraries that we could improve upon and build upon, but still have the challenge of figuring out how do we make all of this work? What are the things that we can use for conference? We built a Terraform provider so people could define their movement plan in Terraform code and run it and see who would get the fastest time. And I think that the whole learning experience was worth it. If I would do this in a semi-commercial setting or just in a more structured way and actually make this, you know, like a after-school club, 100% ROS too. Never go down the rabbit hole of writing this code myself again. Sorry.
I was wondering, I saw that you were using a YOLO model. Which version you're using, if you're using one of the pre-trained COCO models with it?
One of the cameras, so yes, great question. 11 currently on the camera, primarily because that's what it was pre-built with. And so for us, it was easier to get that. And for people detection, all we care about is there a person or not? We don't care whether that person is happy or not. We do know, we can infer from our own experience, if it hits your leg, the person is not going to be happy, but there was no training needed for that. A lot of treatment though. So ultimately for us, that approach was easier. But of course, the cameras are all open source, the hardware is open source. So once we decide that we want to put a different model on there, that's what we're going to do. We've been experimenting with a version of these that we call L'Explorer. So basically the idea is you build a small scene on a table like this, on a smaller one than this, like Lego figures, like, you know, a giraffe sitting in a train. You drive the robot past, it sees that, and then turns that into a visual storytelling device. So for kids, you build the scene, and, you know, like, you now get the story where your giraffe is a heroine that saves the town by driving the train and picking up all the kids from school, something like that. Definitely requires custom models because most models are not trained on Duplo figures. But yeah.
And did you happen to train anything so it would recognize itself, like one of the other versions that you had running around?
We have not currently, well, they do recognize each other in the sense that obstacle,
Yeah.
but not in the sense that I see the other one here, I can do something with it in a visual way. Through Swarm Logic and ESP Now, they can connect to each other, they just don't know who's who, which the way we want to solve that is by giving them different colors, because then with shape plus color, you should be able to detect something. Another thing we looked at is, and Matthew and I joked about this, we should install one of those infrared flashlights, because with infrared paint, you can put a specific marking on there that if you recognize that, nobody will ever see it, but the robot sees it, and that's what matters. One of the bigger options to build, also a lot of fun. But yeah, it would be nice if they recognized each other and knew that the green one has the arm capability, whereas the blue one has the, instead of the arm having a gripper, has a camera on top. That might be a scale for next year.
So I apologize, I missed a little bit of your presentation, so I might say something that you might need to repeat. But so you open source this project and we could do PRs. Do you guys plan to do like some people, they don't want to build the whole robot up and then do PRs. Do you guys plan to do a simulation or something we can use to...
Are you thinking digital twins?
Yeah, like a digital twin, exactly.
We looked into that, mostly because 8 years ago, working at the Amsterdam airport, when you work with sewage pumps that are $500,000, you have to have digital twins for everything, because firmware upgrades can get really shitty, pun definitely intended. We don't have enough data to build one, despite many IIoT vendors saying, just upload a JSON file and we'll give you a perfectly functioning digital twin. So the way we cheat that is, ultimately it's an ESP32. So that's what we order, a strip of 20 of those off of Amazon. We can still run the same commands. Obviously, if there's no motor attached to it, they won't behave, but at least we can test that the code works. So even when we were on a flight, if you pull this one out, people are going to have questions. Very likely the air marshal would like to have a word with you, which is understandable, right? I mean, it's a black device. It's not a common sight. Whereas if you pull out one of the, let me see if I have one with me, one of these tiny dev kits, you can still write the same code, test the same code, and nothing happens because nobody sees it. Not a digital twin, it's more a physical twin.
Yeah. You're just testing the signals out to make sure everything's
Yeah,
good.
exactly.
Gotcha.
It's definitely a cheat mode, but it's also the cheaper cheat mode, because frying this one versus frying that one, just replacing it is annoying. So, yeah, I'd prefer to have a complete virtual version of it that I could run all commands against and see, is the arm working in the way I expect it to? Because of course, you write some code for a gimbal and the arm extends, and then you're like, oh, well, that's great because it's mounted to my desk. When it's mounted to the device and it extends too far out, it tips over, and then you end up like Athena, which is not a great feeling. But yeah, if you have any idea on how to do digital twins, definitely would like to pick your brain.
Okay, awesome. Thank you so much.
Thank you.
Okay. So the software is open source. Is the hardware also open source, or is it just something that you can attach onto any hardware that works, that's compatible with the ESP?
So you can use pretty much any pulse width modulation-based motor. I would highly recommend getting these ones. The reason we bought commercially available hardware is because it's in plenty supply. Adrian lives in Paris, I live in Amsterdam. We had a team in Orange County also working on it, well, team, 2 people. All of us could get the same hardware easily delivered, and when we broke it and drove it off the table a couple times, we still could get easy replacements.
So it's completely possible to 3D print a chassis for it, for example, and use the software you provide?
There's an STL available. There's a, what's the other one? Something in USDC format. If that works for you, let me see if I can pull that one up real quick. But the long and short story is yes, you can, which is where this gets a lot more fun. Though I would recommend not printing a chassis that's not out of metal, simply because of the speed of the device. And let me see. What were all the injuries? Sorry?
I said, what were all the injuries you guys suffered? Toes?
Cut open finger at the top, grabbing one of the chips on the wrong end and puncturing the skin because, well, there's a reason we now have tape on these, and blank headers, because we truly care about keeping ourselves sane. Let me see if I can get that moved over, and if I can get my cursor somewhere. There we go. So with this, you can just explode it. Actually, you know what? We're gonna use a real program for that.
Did one of you guys do that? Is this AutoCAD or?
Oh God, no. Building this from scratch is at least beyond my skill set. Modifying it a little less hard, but basically Waveshare, who makes these robots in different flavors, has all of these things available, which then allows us to pre-print or reprint the parts that we care about, and also customize them. All of them are black, but if you need a different powder-coated one, it's easier to just send the specs to somebody and get the case instead of taking it apart. And the software, initially when they released it, their demo software was basically a zip file they uploaded to the site with crappy documentation. After some prompting, they licensed it under GPL, which made it possible for us to fork it, make contributions, push those back. 9 months on, our PRs have still not been reviewed, so we decided to just open source our version of the code and bring the code to other people that way. Lots of good injuries, and each injury is a learning. I think the hardest part is because it's 2 millimeter thick aluminum. When it tips down and hits your toes, you're gonna feel that for the rest of the week. Worth it though. Let me see if yeah, that and the acrid smell of burning plastic. It's the beauty of working with hardware. You get to debug and use fire extinguishers. But yeah, definitely, if you want to 3D print your own, models available, do it. It's good.
Any other questions? We're at time, but it's lunch break now, so if anybody has one more last question, we can do that. If not,